We have action. We're going to talk about reaction rates today. Kinetics is the study of reaction rates and the factors that affect them. For example, surface area is one factor that affects reaction rate. That's why in your previous lab, I said don't ball up the magnesium because less surface would be available to react with the hydrochloric acid. So surface area is one factor that affects reaction rate. And we'll talk about these factors as we go, and then probably next time we'll link them to the collision theory because everything goes through the collision theory, and we'll talk about how particles have to hit one another with enough force to overcome the activation energy and how molecules have to be oriented properly. All right, so the questions we want to consider: how fast does a reaction go? That's important. If a reaction is too slow, it's not going to be effective, and you may not be able to complete the reaction in the time frame. How much reactant is consumed or how much product is formed in a given time. And this is something I hope that you saw from the POGL packet. You know that reactants get consumed, so their concentration per time will slope downward like you saw in the POGL packet, whereas with products, their concentration will slope upward and eventually plateau when the reaction has reached equilibrium. Are there ways in a reaction can be sped up or slowed down? Sure. We heat up a lot of our reactions. Heating up reactions cause particles to move faster. They're more likely to collide effectively, hence an increase in reaction rate. Increasing the concentration is another factor that can increase concentration. If you ran around in here blindfolded, the chance of you stepping on somebody else's foot, pretty high. If we invite all the kids on this top floor in here, the chance of somebody stepping on your foot increases greatly. So an increase in concentration, generally speaking, results in an increase in reaction rate unless you have zero or negative order. And we'll talk about that too. And we already mentioned surface area. The really new piece, different from honors, is how reactions occur at the molecular level. So we're going to be looking at the mechanism. We won't see this today, but you'll see it next time. And at first glance, you'll be like, oh gosh, here we go again. But it's really pretty easy. A mechanism is, for example, if I wanted to go from here to the back of the room, if there's a lot of stuff in my way, I'm going to take little steps to get around whatever's in my way. So I might go from point A to B, point B to C, point C to D, and then I'm back to my final spot from A to D collectively. So you'll get a series of smaller steps that allow the reaction to occur. And we'll be looking at the reaction mechanism. You can see that with the hurricane now as well. Rather than just going in a straight line from point A to B, it's just going here and here and here until it waxes but good Thursday night. One factor that determines whether a reaction occurs is kinetics. Does it occur fast enough? But the other factor is thermodynamics, and we'll talk about thermodynamics in the third 9 weeks. Now, I interchange these two chapters in terms of teaching. Usually you do thermo next. The kids find thermo a little tricky, and I think we've been through a lot already, so I put kinetics in here because I think it's super easy. It also covers all of Big Idea 4, and we'll talk about the big ideas a little later in the year so you can see where everything fits in terms of the AP exam. So how fast a reaction goes is not the only criterion in terms of whether the reaction will go. The other factor is thermodynamics. Is it thermodynamically favorable? And we'll talk about that much more in the third 9 weeks. Those of you in or having taken AP Bio, you would have learned about spontaneity or exergonic type reactions. Okay? So a little bit, again, kinetics, I said, is the study of reaction rates and the factors that affect them. We'll also be looking at the sequence of molecular events, that is the reaction mechanism. The factors we've mentioned already. The most important factor is the chemical nature. If you put two metals on the desk, they may wave hello to one another, but they are not going to react with one another. Certain substances will never react with one another regardless of what you do to the temperature, surface area, etc. So that's the most important factor, because if two substances don't react with one another, it doesn't matter what you do. Temperature is another factor. We mentioned that. We're going to review the Boltzmann distribution so that we see the effect of temperature in regard to that distribution that you saw in the gas law chapter. Surface area, concentration, catalysis. And then in terms of surface area, you know, for example, we talked about magnesium not balling it up. If you go to a restaurant and get a drink and it's not sweet enough for you, you might put some sugar in there. They don't give you sugar cubes, they give you granulated sugar. If your cube and your granulated sugar has the same mass, which one would dissolve first, the cube or the granulated? Granulated, because it has greater surface area. You have more sites with which you can collide effectively, hence increasing reaction rate. And we'll talk about catalysts a little later on. The first thing we want to do is show how you can express a reaction rate. And just be careful here, because the terminology here gets a little bit murky. In regard to reaction rate, we're talking about a change in concentration either of reactants or products per unit time. Concentration molar per unit time. So your unit's typically going to be molar per second or molar per minute if it's a slower reaction. Shown here is the hydrolysis of sucrose, a disaccharide, to generate two monosaccharides, glucose and fructose. These both have the same molecular formula, but they have different structural formulas. Somebody who's diabetic can't have a large intake of glucose. They can have fructose in moderate amounts. These substances actually have the ability to interconvert, so you wouldn't want too much fructose either. But if you look at like diabetic cookies, if you want, they'll be fructose, not sucrose. Sucrose is table sugar. You can look at the rate of disappearance of sucrose. That's the change in concentration of sucrose. So for example, if you start with 1 molar and you go down to 0.5 molar, you would do 0.5 minus 1, hence the change over the time period you measured. You can write it as concentration of sucrose in the second experiment minus the first, or the second time minus the first, or more commonly, change in concentration. These brackets here mean concentration over the change in time. And the rate overall is positive. The rate of disappearance is negative. I'll point this out in just a second so you see where these numbers come from. You also can look at the rate of appearance of a product. Products get made, so they appear. Change in concentration of glucose or fructose concentration. Change in time. So that's what we're looking at here. And the rate of disappearance here as shown. And I think that's fine. Let's take a look at how you would write a rate equation. This is a rate equation, not a rate law. Be careful, rate equation. And this should look familiar to many of you. For those of you where it's brand new, it's very, very simple. So don't panic. Here's your equation. Lowercase letters represent stoichiometric coefficients. Uppercase letters represent reactants and products, respectively. When you write a rate equation, you can set reactants equal to one another, you can set products equal to one another, you can set reactant and product equal to one another. There's a lot of ways you can do it. Whenever you do a reactant, you always have -1 over the coefficient of the reactant, change in the concentration over the change in time. -1 for reactant over the coefficient, change in concentration per change in time. Products have a positive 1 over the coefficient, same thing, positive 1 for product. The reason why reactants have this negative 1 here, the overall rate is positive, but this value here is negative because the substance disappears over time. So the second concentration is less than the first. Hence a negative value in here times a negative will make a positive. Let me show you how to write one, for example, for the reaction you just carried out in the laboratory last week. So for example, we reacted magnesium with hydrochloric acid to generate magnesium chloride and hydrogen gas. This is the reaction that we carried out. If I want to write a rate equation, again, note the nomenclature, that shows the disappearance of a compound and the appearance of a diatomic element that is very straightforward if you know what a rate equation is. A rate equation will start with rate a reactant disappears -1 over the coefficient. Which compound disappears? HCl. Coefficient there is 2, hence the 2. Change, concentration bracket, HCl over the change in time is equal to +1 over 1 change in concentration of hydrogen gas over the change in time. And again, this value here, and you'll see this momentarily, is negative. A negative and a negative makes a positive rate. That's a rate equation. You can write it from the chemical equation itself. You may be given values for one of these and have to find the other one. Sometimes you actually have to find the top piece, the bottom, etc., and I'll walk you through that. Rate equation. So that's the first main understanding you want today, is the rate equation. Yes, yes?
Yes.
Yes? And for some of you, you're remembering, right? Makes you feel better. And for some of you, I know it's brand new, but it's not hard. Okay? And I will say this. I remember last year that when we were covering kinetics in honors, a lot of the kids were out. So I did a tremendous amount of filming for my honors kinetic stuff. That's all on your YouTube channel. Your YouTube channel you can access. It's got videos just of my honors class in AP. Unfortunately, it's one channel, but AP lectures are labeled APC. And if you go on the Edline page, links, it'll be the last link because it starts with a Y. All right. The average rate of the reaction is as it sounds, an average, a rate in which you have a change in the amount or concentration or pressure or anything per unit time. But you're going to have a time interval. It's not going to be one point in time, so it's going to be an average. For example, it says that in decomp reactions, as well as many other types, the reaction rate is fastest at the beginning and then it slows. And this is what you saw in the Pogel packet. It's really quick and then it levels off. It's really fast in forming and then it levels off. And that's because as you have utilized more and more material, what's going to happen is there's less material to react, so your rate's going to slow. Typically, rates are calculated as an average. So if you have this hypothetical reaction in which A and B are reactants and they react to form products C and D, you can calculate an average rate. Oh my gosh, my thing disappeared. Oh no, it didn't. I see what happened. Okay, so it says, suppose at some point during the reaction, the concentration of D is 0.3, and 2 minutes later, D is 0.4. If I didn't give you the reaction, how could you tell that D is a product? Because the concentration of it or the amount of it per volume increases over time. It says, what is the average rate of the reaction? Okay, very straightforward. Rate equation is right here. I think this is going to block it out, but I'm going to shove it to the back. Why won't it go back? Stupid thing. Oh, gone. Here's your rate equation right here. Be nice if I could draw, right? Can I draw? Should have like a little pencil, right? Ah, forget it. I need my iPad. I'm going to draw on my iPad. Right here, rate equation. Now I'm going to find the change in concentration of D. I started at 0.4, I had 0.3, I subtract the 2 and I get 0.1. 0.1 over 2. Now make sure you can do this in your head. 1 over 2 is 0.5, so 0.1 over 2, move the decimal 1 to the left, is 0.0500 molar per minute. Average rate of reaction. The rate of formation of C, I can write a rate equation for D and C. I know what D is, so I'm going to plug that in right here. It should be plugged into the whole thing. That's why it looked like something was missing. Maybe it would be better if I did, maybe. That just made a big mess. I'll fix that. That's okay. Well, it's not beautiful, but we'll get over it. So now I'm going to solve for this piece. You can call this X. I'll do one out for you, slowpoke, so you can see it. So basically, you're solving for X, so you multiply both sides by 2. The rate of formation of C, which is this piece, then is 0.100 molar per minute. So let's do this one together in slow-mo. It says, I don't like that one. It says, I'm going to pull it to the top. suppose that at some point during the reaction the concentration of B is 0.4 and that 3 minutes later it's 0.1. What's the average rate? Okay, let's take a look. First thing I'm going to do is figure out that rate. Rate is equal to -1/1. Why did I do that? Because it's a reactant, and reactants start with -1. Change in concentration of B over the change in time. So we can just put a big negative in front of it. And then I've got 0.4 molar minus 0.1 over a 3-minute time interval. That was a little sloppy because I did, who stole my whiteout? I know where it is. It's hiding in the drawer. I decided to hide things. I'm just going to be a stickler for this only because of sig fix. So that's going to be 3.00 minutes. I've got negative of a negative, right? 0.300 molar over 3 minutes. And again, 0.3 over 3. 3 over 3 is 1, so that's going to be and that's the rate at which B
shouldn't it be 0.1 minus 0.1?
Yeah, it should. Should we fix that? Yeah. How come it should be that way?
Because you have to take the change.
Because it's losing. You can do it the way I did it, but what would you have to put in front of the 3? Yeah, so let's just do it. Funny thing is on your Poggle I did the same thing, and then I fixed it. Well, initially I put the negative here, but I figured it'd be confusing. So yeah, just make sure you're consistent. Good job. For you guys, not me. All right, what is the rate of formation of C? So you have rate is equal to, C is a product, so we have +1 over its coefficient, change in concentration of C over change in time, and we'll set that equal to the B part, -1 over 1, change in concentration of D over the change in time. So this whole piece here is this, and that's equal to 1/2. I'm going to call this piece X. So X then is equal to 0.200 molar per minute. All right? And this part may help you in the Poggle packet, like 10, 11, 12. Question 10 was worded quite kind of funny. You can omit that one if you want. You were pretty much going after the one that had a coefficient of 1. And I did post those answers for you earlier today.
Is the 1/2 supposed to be 2? Because it's 1/2 times.
No, 1/2. So when you solve for x, you multiply both sides by 2.
I thought it was a multiplication sign. Okay.
Oh, this?
Yeah.
Well, okay, so I'll make like a squiggly x. Is that better?
Yeah.
I usually do make squiggly variables, but then the kids are like, what's that? Almost looks like a lambda. That's a lambda. Lambda. Does a lambda have a B?
Yeah, I think so.
Where's D?
Or is it lambda?
I think it has a B.
I think it has a B also. Once upon a time, I used to be a very good speller. I won my spelling bee in 5th grade. I beat the 6th graders, because our school went K through 6. You guys go K through 5. Alrighty. So usually we do average rates. You can do instantaneous rates. That would be at a particular point in time. So you could just make the tangent line to the curve, and I can show you that. I don't think you'll see much of that, but sometimes you never do know what they're going to ask. I'm just going to open up your PowerPoints for a minute. So what we've got so far, kinetics, is the study of reaction rates and the factors that affect them. You know how to write a rate equation. You can get an average rate. You also can get an instantaneous rate. And one thing I would say is over your nice long weekend that hopefully is not without power, but certainly you have your book which you're sleeping with to keep it safe. You have a ton of really good practice problems, and you'll need a few of these to get good at it. All right? Come on. Open, open, open. How come it takes so long? Because I have too much stuff open? I really don't.
These computers are the worst computers.
Well, do you think it would open better? I don't have that much stuff open. I usually have much more open. Here's an older version. Just doesn't want to open. What is OneNote?
That's where all the Microsoft stuff is in one.
I wonder if that's the problem. Well, see, I can't even get it from the book because I can't move that thing. It's stuck. This is an older book. This is kind of tricky, kind of a messy curve, but we'll take a look at this one until the little thing's open. It's stuck. What's shown here is the same type of curve you saw, concentration versus time. If you look at the black line, that's the true data, and the fact that the concentration decreases over time tells you that hydrogen peroxide is a reactant or a product. Reactant is correct. If you wanted an average rate, you could do so over a time interval. For example, if you wanted to know from 60 to 180 seconds, you could go up, and then you could do 0.7 minus about 0.46, subtract the 2 and subtract that 2, or that would be an average. If you wanted an instantaneous rate, you would basically get it at a specific point in time. You could make a tangent line to the curve and then get the slope of the tangent line. And unfortunately, this is not shown so well in this book, I think there are better images in your book, and I'll show you that at the end when I pull the iPad off. But if I take it off now, then I'm going to mess up our video. That would be awful. All right, so instantaneous versus average. The other thing that we really want to talk about today are rate laws. Rate laws are extremely helpful. They are different from the rate equations. They are derived or integrated, similar to what you see in calculus. All right, so you know how to do derivations. Some of you probably don't know how to integrate yet. Right, you know how to make derivatives. Same thing, like in calc, you know, what did I say? Derivations is a derivative. Same thing.
It's just weird hearing it be called derivation.
If you had 2x squared, the derivative would be 4x. See?
Wait, okay.
See? You got it.
She's not in calculus. That's why I don't know how she
Doesn't matter. She knows how to do it. And she was so excited. She's like, I know this. That was so good. All right. So with rate laws, this is going to relate the rate that we just talked about to the concentration of reactant only. No products in here, and you don't have molar per second. You just have concentrations. Christian, if you pull that, it's going to make such a mess. But don't you worry, if you accidentally pull that, I turn the videotape around and I film it so everybody can see. No.
Miss Dublin, have you ever seen the school
Yes.
Miss Dublin let us pull at the end of sophomore year.
It's not a good idea on the second floor. The water rushes through. A lot of it doesn't go down the drain. It crashes through our floor, through the ceiling. Whose classroom is below mine? Is it Pocabler or Dublin? Is it Gailey?
No.
Well, they would get a shower like they've never seen before. Anyway, shh. Come on, guys. This is great.
I think it's
Here's your general equation. Lowercase letters, coefficient, uppercase letters, reactants and products. This is what a rate law looks like. Rate is equal to K. That's a proportionality constant. We'll solve for it this year and you'll figure out its units. Concentration of reactant raised to the N. N is the order with respect to A. I'll explain that. B is the order with respect to B. If you have 3 reactants, you'd have C to the L, D to the K, etc. It starts at the middle of the alphabet and works backward. N and M typically are 0, 1, 2, 3, but they can be negative and they can be fractions. If they're negative or fractions, you probably won't have to do the math of it, but you could get a negative or a fraction from a mechanism. Not hard, it just looks funny to the quiz. And I remember in 2000 and I want to think it was 9, after the kids took it, maybe 2010. I think it was, I know who it was. I'm trying to think what class she was in. It was 2009, I think, where the kids came in and they're like, oh my God, I think there was a fraction. I'm like, and I looked at them like, this is so easy. They're like, but we don't want fractions, so we didn't make one. I'm like, oh no. So we'll make sure you know how to do fractions. I'll show you the question. All right. The exponents have to be determined by the data. They do not come from the balanced chemical equation. Don't worry, someone will do it.
8 knots.
N and M are going to establish the order. This is a little bit tricky. I'm going to give you an example so that you understand rather than reading through that yucky stuff. Let's say, for example, that you have an equation A plus 2B yields 2C plus D. The rate law format would be rate is equal to K, A to the N, B to the M. N is the order with respect to A, M is the order with respect to B. So if you have rate is equal to K, A, B squared, what's the order with respect to A? 1. With respect to B? 2, or you'd say first and second. The overall order is the sum of the exponents. 1 plus 2 is 3. So you'd say third. Okay? Now, if you had the rate is equal to K, A, B squared, if A is doubled, I'm going to put a 2 where the A is. Then the rate doubles or increases a factor of 2. If A is tripled, I'm going to put a 3 in. What happens to the rate? Exactly. It triples or increases by a factor of 3. Now, we're going to leave A alone. Nothing's going to happen to A. And let's say if B is doubled, we're going to put a 2 where B is, and the rate quadruples. Increases by a factor of 4. Good. Now let's say if B is quartered, careful. Yeah, this gets into the exponential, 7th grade advanced math, guys. Come on, we can do it. All right. So that would equal, so it's 1/16 what it was, which sounds pretty retarded. So we say when you get a fraction that's less than 1, the rate decreases by a factor of 16. That's the reciprocal. I'm going to get rid of that mess. Well, you can do sneaky things. Like if you had A being halved and B halved, you'd have 1/2 times a quarter is an 1/8. The rate would decrease by a factor of 8. But you can get sneakier because if you have a 3, like let's say you triple, you can't see. Let's say you triple A, so you put a 3 in here, and you half this, so you'd get 3/4. So there, it's a little factor of 4/3. But you'll never get it wrong again. Yes, because you initially got 3/4, so it sounds retarded, yeah.
I got that one on the test. You remember that?
Yeah.
That question.
If you calculate it out here where the rate was 3/4, it's 3/4 what it was, or decreases by a factor of 4/3, the reciprocal. All right? So that's a lot of variation. So that's what order means. And we'll be doing more of that, so don't panic. All right, I think I hit a lot of it. K is the proportionality constant, and you calculate K from the rate and the concentrations. I'll show you how to do that. K is temperature dependent, and a catalyst can affect K as well. We'll come back to that. Now the units of K depend on the order of the reaction, and I'll show you how to derive units of K, but units of K can always be determined very simply, knowing that the units of K are molarity, 1 minus overall order, time to the -1. So for example, in the rate law I gave you right here, you could determine the units of K because it's molar 1 minus overall order. What's the overall order? 3. 1 minus 3 is?
2.
Really? Who said 2? You're in big trouble. That's okay. Sam and I were doing a lot of practice adding and subtracting with negative numbers. She thinks I'm crazy, but every morning on the way to camp, I would drill her at least 20 questions. And after a couple weeks, she got it. And then she didn't have to talk to me. She was happy. Just kidding. No, I really did drill her. Molar to the -2, time to the -1. And I hope we don't lose computer access because she could do like 8 math lessons over the 4-day weekend. All right, let me show you how to do one of these, and then we'll take a break. You think I'm joking? I love 7th grade advanced math. It is easy. For you, because you know how to do it.
I thought it was so 7th grade too.
Seventh grade, I didn't even take seventh grade advanced math. I started out taking it and then I switched out.
Yeah, I didn't take
Oh my god.
All right. This looks awful. I promise. I promise. It's really easy. All right. Now, here comes the good news. You have to be able to do it without a calculator. Here we go. Yeah. I think I'm also on Edline going to put a little mental math sheet for you. I think it would be very good over the 4-day weekend. All right, ready?
Yes.
Here we go. We've got a synthesis reaction. We've got initial concentrations of both reactants, and we've got the initial rate of formation of the product. We've run 3 experiments. And what you can see here is that we've held concentration of nitrogen monoxide constant, varying the concentration of chlorine, and we can then examine the rate of formation of the product to look at the effect of this reactant on this product. Similarly, we've held chlorine concentration constant. We've doubled this concentration, and we can look at the effect on the rate. The goal here is to determine the rate law, to figure out how altering the concentration of one reactant at a time affects reaction rate. We're talking about kinetics, the study of reaction rates and the factors that affect them. So the factor we're looking at here is what? Concentration of CO2 and of nitrogen monoxide.
So it's your A and B.
Say it again.
So it's your A and B.
So it's your A and B?
Yeah.
Reactants. Yes, 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 yes. So we're going to try and determine the rate law. The rate law is going to look like this, but we want to figure out what N and M are, okay? For those of you who have seen this before, this is going to be much easier because you're probably just going to have two reactants. And I know this looks like stuff you can't do in your head, but you can. All right. When I do these, there's not a golden rule. There's not a stepwise process. You just look. I look, whatever pops at me first, I run with. Right away, somebody said 1 and 2. What is 1 and 2? Who said it? Go ahead.
They're constant.
What's constant?
The concentration of NO.
Right. So in experiments 1 and 2, the concentration of nitrogen monoxide is constant. So you can look at the effect of chlorine concentration increase on the rate. Your approach here, concentration of chlorine in experiment 2 over experiment 1 raised to the M because it's the second reactant over the rate of the second over the rate of the first. And some kids are like, well, what do I put on top? The big number. You don't want to deal with fractions. These are always going to come out perfect. You don't have to do logs here. Divide this over this is 2 to the M. This over this is 2 as well. 2 to the M equals 2. M is equal to 1. First order with respect to chlorine. Sometimes in a different color I'll put a 1 here because I know the order with respect to chlorine now. And I'll do one out in its entirety so you can see. Now you're going to try and look at the effect of altering nitrogen monoxide on the rate. So chlorine is constant in which two experiments? 1 and 3. So I'm going to look at the effect of nitrogen monoxide. I'm going to put the big number over the small number to the N, the rate of the third over the rate of the first. Whatever experiment is on top here must be on top here for the rate. Divide 2 to the N is equal to 4. N is equal to 2. Now I will say one thing. Your exponential math has to be good. What's 2 to the third?
8.
Good. 3 squared is?
47.
3 to the third is? You're just ahead of me. 3 to the third is? 27. All right? And it's really, 4 squared is?
16.
You'll be good. Because this will be non-calculator. Here we go.
2 to the 10th is the top.
You now know both exponents. Here's your rate law. Now you can calculate K and determine its units. Its units are very simple. Capital M, 1 minus over order. So 1 minus 3 is? -2. And the time they gave you, I believe, was seconds. So seconds to the -1. There's the unit.
So that's your K.
That's the unit for K. To get K, you just manipulate this. You divide both sides by the concentrations raised to their exponents. You can pick